All right, so today, thanks for coming. I'm going to talk about, I do different things. Most of the science I do via my students. And I'm not going to talk about that work today. Let them talk about it at some point. I'm going to talk today about a program I'm doing for which I'm doing mostly technical work, meaning stuff that makes sure that we can actually observe the things that I'm talking about. But I thought I would describe the program as a whole, why we're doing it, and all of that. So what we're talking, and I won't really talk, I mean, I do have like one page on what I actually do, but hopefully we will get to it, because it's quite boring.
I apologize. Sorry, can I make a mask announcement? I forgot.
Yes.
Under current NWE policy, masks are not required in situations where attendance is optional. And I think this counts because there's a Zoom. So if anybody, I think the audience and speaker can remove masks during brown bags. If anybody feels uncomfortable about that, you can let me know privately and we can revisit it, because I don't want to make anybody uncomfortable. So let me know if that makes anybody uncomfortable. But otherwise, we'll be optional.
All right.
Sorry.
That's all right. And what I'm going to be talking about is an all sky, really, time domain-ish, stellar spectroscopy. This means about stars. Survey. And this thing has a name. It's called the Milky Way Mapper. It's led by Jennifer Johnson and John Bird and many other people. And it is part of the Sloan Digital Sky Survey 5, which is a bigger project which does this plus some more stuff. This is led by Jim Kohlmeyer, who's at CETA now, and Hans-Walter Rix, and many, 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 many other people. And what I'm going to talk about today, and just the broad parameters of this. It's 5 million stars. And you get chemical abundances, ages, motions, lots of information about each star. And I'm going to talk.
And by motions, you mean like velocities in space?
I mean radial velocities is what you get from this. I'll talk about why we do this. I'll talk about how we do this. I'll talk about what we actually are doing. I won't talk too much about who. I'll just say it's lots of people. There's probably 100 or 200 people who are devoting a lot of their time to making this happen. If you look at people as committed as myself and above, it's certainly a very large number of people. So there are lots of people doing this.
I think you're also going to probably talk about where.
I will talk about where. I did write that down. I'll also talk about when, and when is now. So we're not talking about the mid-2030s, we're talking about something happening right now.
Okay. How does this fit into the bigger Sloan universe?
Oh, this is after 4 and before 6.
We're now. 6.
God help me that I'm going to 6.
5 is now?
5 is now. 5 is, yeah, so I was the director for 4, which operated between about 2014 to the beginning of 2021, and then we just had our final data release at the end of 2021, and so that's over. And since about late 2020, SDSS 5 has been taking operations. I'll talk about timelines in a little bit, and you'll see like the length of the project is more than the time you're actually observing. Because like you observe with an instrument, you first have to build it, things like that.
And will it continue indefinitely? Will be like 10?
So I say this, we are partially funded by the Sloan Foundation, and I always, in my head, the Sloan Foundation treats us a little bit the way that like Dread Pirate Roberts treats Wesley. It's kind of like, good job, see you in the morning, or we're gonna say, good job, sleep well, I'll probably kill you in the morning. But then we seem to keep going anyway. Anyway.
But the thing I would say, to answer that from my perspective, each of these projects is a very large fundraising operation. So they're always, we never know it'll continue. And I think Mike deserves a lot of credit for the funding we got for SSS 4 and some of the credit for the funding we got for SSS 5.
But from instrumental point of view, it's just an upgrade of existing thing, or every time?
I'll talk about what it entails, but the main point is that we keep going as long as there's something interesting to do. And if you want to talk about programmatics, one of the interesting things about this program as a whole is like if you go to like the APO 3.5 meter or some other telescope, typically it's funded, it has some funding line that it gets and that gets continued year to year by default, and people apply for programs, and for time, and then they come do their observing, and it just sort of rolls onward. Whereas this is like, if we don't find something interesting enough to do to raise money for a big project every 5 years, the thing's just going to shut down. And someday that will happen, right? Someday it'll be like, no, you really can't compete. So one thing that happened between 4 and 5 is that we used to do redshift surveys. That used to be a thing, galaxy redshift surveys. That used to be a thing SDSS was really good at. Did it for 20 years. Got several times as many redshifts as any other program. Well, in the last year, DESI has gotten several times more redshifts than SDSS ever got, right? And so in 2019, we were like, it's probably time to stop this because DESI's on the horizon. We have to find some other interesting thing to do if it exists. And there's always a possibility if there's not, and we'll all go off do more interesting things. But that's been the general philosophy, which is has a lot of upsides and a lot of downsides. Because it's like you keep doing you're driven to do like very interesting, compelling things, but also it's existentially terrifying when you're trying to figure out whether or not that thing's going to happen. Right. Anyway, I could go on for a long time about that subject. But why do we do this? So I always think the reasons why we do things in a shape like this, where like the big important thing you want to do with your life is up here, and then somewhere down here, it's like you wake up in the morning and you look at your screen, you're like, why is there an attribute error on line 556? And there has to be something connecting that problem you're trying to solve to the big thing you're trying to do overall. And every morning you should remind yourself of this chain of motivation.
He's an optimist.
So it gets me up in the morning. It's how do galaxies, stars, planets, all the way down to us, form? What was the process by which all of this happened? Right? Cosmic origins, NASA calls this. Should have this in the first paragraph of all your NASA grants. And that sort of motivates, our study of cosmology. I know some people do this because, to figure out the physical laws and stuff like that. But this is another reason to study cosmology. The growth of structure, meaning like linear structure, those scales. And then on the smaller scales, galaxy formation. And if you want to study this part of it, which is the small scale stuff, the stuff that's happening, within a galaxy, what is the process of these stars forming within the galaxy? How is star formation regulated? There are lots of galaxies out there. We study them, the whole population of galaxies, and that's one direction you can go, and we study in other contexts. But there's one galaxy we can measure better than any of the others in many ways, which is the Milky Way. I'm going to concentrate actually on the disk of the Milky Way, the thin disk, which is still forming stars in the Milky Way, because you can do very, very exquisite observations of it. You can like measure individual stars, right? You can measure some like substantial fraction, like 0.1% of all the stars in the Milky Way, and that makes it an interesting thing to study, and then to better understand, the other galaxies, like the full population of galaxies. And what do we want to know? What are we trying to measure? Well, the things we care about are the star formation history. This is going to, this is how all this happened. Chemical enrichment, right? Because it's in these stars that most of the elements heavier than helium formed. The mass distribution, and this will, the mass distribution also has the dark matter. So when you're measuring the Milky Way, you're measuring something about the dark matter distribution, but you want to know the assembly of all this, the assembly history, right, which is somehow distinct from the star formation history. Star formation history is like when the stars formed. The assembly is like when it all came together. So to study this thing, we want huge numbers of stars with the stellar properties and the motions. And this is why the apogee instrument was built. To study huge numbers of stars. And the key things about this, where it's, actually we can raise this up, it's high resolution. It's near infrared. It is multi-fiber. It's wide, it's on a wide field telescope, actually one in the north and in the south. And as I'll explain in a second, we want these things in order to get a huge number of stars in the disk, in order to measure the star formation history, enrichment, mass distribution, etc., in order that we can figure out all this other stuff above there.
Are we going to get to that attribution error? Because I'm excited about that.
No. I haven't figured it out. And this I should mention right now, this thing here, this instrument, which takes these spectra, is highly complementary, and to another data set I can't talk about this subject without mentioning, which is that from the Gaia satellite, which measures parallax tangential motions. The spectrograph measures Doppler radial motions, but Gaia gets the other 2 dimensions of motions. And it also has spectra and lots of other things. But point being that you will have these things for all of these apogee stars too, so you're really getting a complete picture of this sample of stars. Okay, that's why we're doing this. Or that's why we want this huge sample of stars, right? But I didn't just say take spectra. I said take high resolution spectra, take near infrared spectra, multi-fiber, wide field. Multi-fiber and wide field are like, you want lots of them, and you want them over the whole sky, as I'll describe. So those seem kind of obvious, but why do we want high resolution? Why do we want near infrared? These are things we should explain. So why near infrared? And the reason we look at the near infrared is to see through the interstellar dust. So, interstellar dust is like this very, very fine-grained silicate type material. It's like a powder. In fact, and it's about, you know, Nick will know better than me, but it's like some fraction like this of the gas mass in the interstellar medium. The medium, there's all this gas in between the stars. About 1 or 2% of that is in metals, meaning things, you know, things heavier than helium, and then about half of that is depleted onto, a border half of that, maybe a little less, is depleted onto these little particles of what we call dust, which is very different than the dust that's floating in this room, which is sort of mostly skin cells. This is this like silicate material.
It's also different from what general relativists call dust, which is which is like a non-interacting gravitational matter.
Yeah, it's like,
So
it's almost the opposite of that,
it is
because
really-
it doesn't have any mass as far as we're concerned.
Correct.
But yeah, that was always super confusing to me.
So they call it dust.
A dust.
I know.
What's the dust doing? It's shining. If we look at the size, I said it's very fine. More specifically, what I mean by that, if you look at the size distribution, like the distribution, like the amount of mass per unit log A, looks something like this, where this peak is like 0.2 microns or something, and this is, you know, and this is declined by a lot before about a micron. And what this means is that if I'm a photon with a wavelength like this, I get to go around the dust, right? Whereas if I'm a photon with a wavelength down here, you know, the dust is very opaque. And if you sort of look quantitatively, people can estimate. Astronomers call this the extinction, which is that how much of the light is absorbed or scattered. And if you look at that, the log of the extinction versus the wavelength, and roughly the same, now I'll just draw the same scale. Oh, let me do this a little differently. I'm doing great disservice to a lot of hard work. This is, you can measure this in a bunch of ways, but you can look at stars individually, and then knowing what an unextincted star looks like, you can estimate the extinction law, and people study this in great detail. But for our purposes, it's just important to know that this is a relatively steep function of lambda because of this size distribution. And the consequence of that is that, for example, if I look at the galactic center, so I look straight through the galactic disk to the galactic center, this extinction is about 10 to the 12 at half a micron, whereas it's about 10 to the 2 at 1.5 microns.
Sorry, what's the unit on the 10 to the 12 what?
Like a factor of 10
Like
to
a
the
factor
12.
of 10 to the 12, okay.
It's like
Yeah,
1
so
over
it's
that.
like, so if there are 10 to the 12 photons that would have hit you, instead there'll be 1. So, yeah, because the rest will be extincted. So it's a very large factor.
Are there brown bag rules?
30 magnitudes, just to translate it into,
Oh, it's just.
into understandable words. Right?
I was just gonna ask if there are rules about magnitudes in
Yes.
this room. I think there are, right?
Certainly.
Lagrangians and magnitudes?
Only real numbers, please. Things that go up.
You're allowed to think of natural log
You
though?
can take an approximate natural log of 30 here. So that's why, if you're looking in the galactic disk, you want to be looking out here, not in the optical. That's why you want to work in the near infrared.
But I have one very nice question. So here, this is just 3 times what? How to measure this power?
What do you mean?
It's 10 to 12 from 10 to 2 to 10 to 12. But I mean, since the match with this power law, you
Yeah, I think to do this, I was saying this is a factor of 3, and so this is
I have the answer to that.
so this is 1/9.
The reason is that this is a dependence of the optical depth, which gets exponentiated to make.
Yeah, this is the log.
oh,
Yeah, it's a log of the extinction that's proportional to this, which still doesn't make these numbers work, but it's okay.
Yeah. And there's some
It's still a
saturation-
large factor.
There's some saturation issues, and it depends on stellar spectra. Like the details of this are a little challenging, but yeah.
So if you follow the math through, you'll actually get that I should have done a factor of 10 to the 9, but it's okay. It's okay. It's still a billion times easier. Not 10 to the 9. So why? Okay, great. We want to work in the infrared, but why do we want to work at high resolution? And I'm not gonna quite fully answer this question to your satisfaction, but I'll give you a sense. What is it we want out of the spectra we take? What we want is we want stellar parameters. Like something we call the effective temperature of the star, whose definition I will not bore you with, but it's basically the temperature of the surface of the star. The surface of the star, which is like the photosphere. There's something called log G, which is basically the gravity at the surface of the star. So it has to do with the mass and the size. Although what you measure is something closer to a density in the photosphere, but that's okay. And then we want to measure an abundance, or sorry, a metallicity, an overall metallicity, which here I'm going to refer to as the iron abundance relative to hydrogen. These brackets, these things equal log relative to solar. So by definition, the sun's metallicity is 0 in this climate.
And it's also in the surface, I guess.
It's measured at the surface, yeah. But, well, it's tricky because what you're actually measuring can be sensitive to the metallicity throughout the star. But basically, yes, it's a surface metallicity. But when you measure it, like the overall temperature of the star, for example, is sensitive to the metallicity. Like the whole structure of the star changes if you change this. And so there, you do have sensitivity to the abundance within the star. So there's some definitional issues that one runs into there in terms of what you're actually constraining. And then what we usually distinguish as the abundances, which is like all the other elements, and usually we think of these as relative to iron, like is what we would call the abundance, right? The relative, basically, there's a metallicity, which is the total amount of these elements, but then you know, you don't always get the same fraction of magnesium versus iron, or oxygen versus iron, or anything else, or, you know, carbon, nitrogen. What are the other elements? The other elements.
Potassium, manganese.
Yeah, there are lots of them. And apogee can measure, I mean, depends on exactly what observations and the signal and noise and the type of star, but it's of order 20 of these elements. And to determine these, you're more or less looking at, you know, lines. So we, in astronomy, if we have a spectrum that looks like this, we will refer to this part of it as like the continuum, and these things as lines. They don't look like lines, they look like dips. But when you spread the spectra out two-dimensionally, if we're a long slit spectrum, they do look like lines, and so that nomenclature is stuck. So these things are called lines. This is wavelength, and I picked a particular range, 1.526 microns to about 1.531 microns. I hope there's not a stellar spectroscopist in the room to contradict me, but this is a small fraction of, say, the apogee wavelength range, which is like 1.51 to about 1.7 microns. So this is just a little snippet of the apogee spectrum, and what I'm plotting is something like f sub lambda. And these lines, they might be associated with different elements, like this one might be associated with manganese, these ones might all be associated with oxygen, this might be iron. And in some general way, the strength of these lines is related to the abundances of these elements. Although it is not as simple as like, oh, if this is twice as deep, there's twice as much oxygen. There's a lot of effects that come in here. But the things you measure are things like what you would think of as the depth of the line, which is the amount of continuum that's absorbed by this line. And then there's also sort of independently of that, a width of the line, not to be confused with an equivalent width, which is really like a depth. but this width of the line and the depths of these lines can be translated into the things we want to know. The density at the surface of the star, the temperature at the surface of the star, and the relative abundances. To actually do that comparison, you have to have a model of the atmosphere of the star where you model the line formation and all of that fun stuff. It's actually all relatively complicated, but you can do it. You can do it at some level of approximation. You can't do it perfectly. But the point I want to make is that these lines are intrinsically pretty narrow. So the line width is generally set by what's known as collisional broadening in the surface of the star, which is basically that, if you think of the line as like as an absorber that's decaying, like the collisions tend to reset that process with some frequency. And the width of this line is more or less directly related to that frequency of which are hit. And then that's really complicated because, like, what does it mean for two atoms to hit? It depends on how exactly they're interacting, whether it's van der Waals or what have you. And so there's a whole bunch of physics that goes into how the local density affects all of these different lines differently, depending on what species they are and all of that. So there's a very complicated story that goes into here, but at the end of that story, you learn that these widths are pretty small. Not as small as the classical oscillator width, which is super tiny, but in astronomer parlance, if we asked what the R of this was, which is the wavelength over the width in wavelength, this is something like maybe a little less than 10 to the 5. So very high resolution. And so if you have two lines that are close to one another, you know, the best you could do to distinguish them would be a spectrograph that did this. If you have a line which really is, its width is really that, just to resolve the line and not have it diluted by the continuum around it through the smoothing of your spectrograph, you need a spectrograph with that resolution. So Apogee doesn't have quite that resolution. Apogee has a resolution that's a little more like 20,000. And so it's you know, as the true stellar spectroscopists complain that R of 20,000 isn't enough, and yet they still seem to use the Apogee results. So that's why you go to high resolution. Make sense? All right. So this Apogee instrument I've been talking about, how did it come to be? I'm going to tell this story, so I'm going to switch gears a little bit and talk a little bit more about how all this happened.
Sorry.
Yeah.
First, related to the why, or I don't know if it's gonna come up, but like, how does this relate to what we already know? Like, this is more stars, or like in near infrared, we already have.
Yeah, I'll
like,
get to
database,
that.
so you will.
I'll get to that in sort of the comparison. I mean, in the case of Apogee, it's really that there was no very large survey of stars in the Milky Way disk before Apogee, because all of the largest surveys were in the optical. And so you couldn't work in the disk. And so you really needed, you know, a many fiber infrared instrument to do a substantial sample at all.
This is the first large IR survey.
Yeah, yeah. And so, right, that makes sense? Yeah. So we were excited about that back when the Apogee people started building this instrument, which was in early 2007, long time ago. These things take a lot. So I looked back at all the brown bags I've given, and it's always a lot, like they really are like SDSS 3, SDSS 4, SDSS 5. And then I was like, that's kind of boring, but it really does take a long time to do these things. They don't just happen on a dime. And the reason we can do the program I'm describing today is because of work that started, you know, really 15 years ago, even before in terms of proposing these things. So this really started being built with this idea of mapping the Milky Way. Most of the instrument building was done at the University of Virginia. Some of it's done in Arizona, some at other places like University of Washington, but the bulk at Virginia. And SDSS-3 started observing in 2008, but this instrument didn't come along wasn't actually ready until early 2011. So it really took 4 years to develop and build this instrument. And it was put on the Sloan Foundation telescope, which is in New Mexico at a place called Apache Point Observatory. New Mexico is in the northern hemisphere. Remember that for later. And this is a wide field telescope. So this is about 3 degrees across, which is about 7 square degrees. This is a weird astronomy symbol for square degree.
That's even less allowed than magnitude.
People do it all the time. Stop me.
Is that really a symbol or is it
They literally write that in paper. It's embarrassing. There's an SI thing for square degree. By the way, what is it? DEG uppercase minus.
I don't know why you would do
Is
that.
two. Oh,
It's very
I
unclear.
didn't know that was
That's
the
SI.
SI. That's what I know. Good.
So
You're a physicist.
So we did a bunch of observing, and then with our infinite creativity, started working on, almost immediately started working on SDSS-4. And SDSS-4 involved continuing to observe in the Northern Hemisphere with this spectrograph on this field of view. But, oops, daisy. But, I just want to get the, also, as I will show later, it turns out that most of the stars in the Milky Way are not observable from the Northern Hemisphere. So we built this whole system to observe them, and then all the stars turn out to be in the Southern Hemisphere.
I think we knew that in advance. That wasn't a discovery of SDSS-3.
That's true.
Could you imagine that paper?
Yeah, so no, it didn't come out on Friday. Lots of others did, but yeah, hold on. So in early 2012, we started building Apogee South. And when I said, so the thing about these programs you have to remember is that when we start the program in early 2012, that doesn't mean like, oh, we have our money now we can build. It's like, we don't have any money. And so we're gonna build, you know, as fast as we can, given the fact that we actually don't have any money right now. So that means these start dates are, you know, we're always doing this stuff at risk, and sometimes it takes a while to actually get going.
Actually, Mike, that point is slightly interesting because that is an interdisciplinary thing between particle physics and astrophysics. In general, particle physics colliders are not done as at-risk facilities. They're done as fully funded projects with well-defined budgets, but these are partnerships among universities where we never quite know whether we can pull it off, and we just go.
Yes, yeah. Thus the aforementioned existential terror.
Can you do science if it's like half done?
No. What was the correct answer to that question?
Officially, no. Officially, the answer is no.
I see.
And so we actually began.
This talk is being recorded up.
And so Apogee South began here, and this was done at a place called the DuPont Telescope, which is at a place called Las Campanas Observatory, which is in Chile, which is in the Southern Hemisphere. And it has a smaller field of view, which is about 2 degrees wide, and something like 3 deg squared, which is a little worse. Well, it's actually a lot worse in terms of field of view, but the weather is a lot better down here. And so actually that partially balances things out. And somewhere in here, we realized 2 things. One of which was all of this work was being done with these spectroscopic plates, meaning you drill this plate. I have a couple over there in my office, where you drill these plates. You have to do it a few months in advance. They get hand plugged during the day, and then they get observed at night. And to change them out from each other takes about 20 or so minutes. And so there's a fair amount of overhead in terms of planning beforehand, and in terms of observing, you know, sort of during the night. Like, you generally expose for about an hour, because if you expose for 20 minutes and then it takes 20 minutes to go to the next field, then you're spending half of your time not observing. and that's not great. And so you're generally driven to these longer exposure times, higher signal to noise, which we'll get back to. And we realized that by the end of SDSS4, we were actually getting to the end of the interesting new things you could do with a system like that. You know, by the end of SDSS4 in 2020 or 2021 as was, you know, it'd be 20 or so years of using this system, and we squeezed a lot out of it. The next generation of redshift surveys was going to robotic observations. You know, that when people thought about, you know, using the aperture instrument in the future, they were, you know, a lot of the programs people wanted were like, well, maybe we want to expose for less and observe more stars. And you can't make that trade-off very efficiently with the plates. And we also realized that these timelines were pretty short in terms of, you know, starting to build something and then bringing it into the survey. So we realized around 2015 that we, you know, which was really just after we started SDSS4, that we had to be planning for the next thing. And so we did that. And it turned into SDSS5. And it really started in mid 2015 in terms of ideas, and then started building a new system in 2017. And the key thing about the new system was to replace these plates with fiber positioners. Robotic fiber positioners that could be quickly adjusted, moved from field to field, so you could take a short exposure and move on to the next field. So you get lower signal noise on each star, but you get many more stars potentially. And so that's the system for SDSS5. And just to give you a sense of what that is physically, instead of this circular plate, we have a hexagonal grid of robots, which I practiced drawing earlier. There are more than this. There are 500 that fill this. And each robot has a patrol area that looks like this. And so the neighboring robot would have a patrol area that looks like this. It's overlapping, right? And then this is filled with 500 of these robotic positioners.
What kind of covering fraction do you get with
Well, it's basically 100% coverage.
But it's not uniform, I guess.
But it's not uniform. And so generally in many places you're getting 3 or 4 robots covering you. So it's one of the advantages of a system like this is you have lots of overlaps, which is helpful for being able to observe things once you think about this. Like if they didn't overlap at all, then you can only observe one thing in each particular patrol area. But here you have more choices to make. It causes some issues because there are more ways for things to run into each other. But luckily we have very smart people who figure out how to make the robots move so they don't hit each other.
How much of a margin do you have to? Sorry, this is probably. Can this mess up? Can you end up getting collisions? And
you certainly can end up getting collisions if you design it wrong, but we don't design the observations wrong. You have to get through a number of layers of checking before things will collide.
Okay.
But very relevant in previous Sloan Digital Sky surveys, because we were doing large-scale structure, we cared in great detail about whether we're covering all separations equally, and we weren't, of course, and that was a big issue. In fact, there were many PhD theses here about that problem.
Oh my God.
But in this case, in the Milky Way work, we care less about the small-scale structure. That's not as But this is very relevant because the questions you're asking are exactly the questions that we would be asking if this was a large scale structure project. And at some point, the kinds of questions you're asking might hurt some projects we want to do in
Oh,
STAR.
it's definitely limiting in DESI,
Yeah.
for sure. And
Yeah,
that's
yeah.
one of the reasons they drive to covering the sky like 5 times, right? Is because, to mitigate that problem. If they were only covering the sky once, the DESI design would be really quite bad. But it's all designed together, so it's basically fine. If I look at this from the side, it looks like this, and this thing can rotate around this axis. The focal plane is here, and there's actually 2 fibers that come down. One is an optical fiber that goes to a Boss spectrograph, and then there's an infrared fiber. I mean, the fibers are the same, but they go to different spectrographs. And then it's these parts that can actually collide in this ring here, in this annulus. And all this is, these are built by EPFL in Switzerland. It's all assembled by the OSU, and then various parts and hardware are made at the University of Washington. Sorry, and software is built at the University of Washington. And this system is the system that SDSS-5 is using. It can reconfigure in something like 3 minutes. So that's good. That's not the only cost in between observations. There's some calibration costs as well and slewing the telescope. But what this does mean is that you can do these shorter exposures, larger area. Okay. You don't have to, with this robotic system, we can make a decision the night before or the day before and say, oh, we want to observe these fields in this way, and then just do it that night. Before, we had to be like, 3 months from now, I want to observe this field in this way, so we're going to have to, send something to the University of Washington to get a plate drilled, and it has to be sent by mail to the observatory, et cetera, et cetera, et cetera. And so this is a much more flexible system. Incidentally, a system which you could run with lower marginal costs than the plate system.
What does the robot literally mean?
What?
What does the robot mean?
I can't hear you.
What does the robot literally mean here?
This thing is the robot, and its robotic functions are to rotate around this axis, and this piece can rotate around that axis. And then if you think about that and the fact that I haven't drawn this quite right, but this is about 7.4 millimeters here, and this is about 15 millimeters. And then if you think about that for a while, that will be able to inscribe an annulus.
So why do we need to do this system rather than just use the former configuration?
Well, because this system can reconfigure very quickly. You don't have, whereas the old system, you had to pull a plate off the telescope, which means you take the telescope back to zenith, and you take the plate off, and you put a new plate on, and that whole process takes a long time. And during that time, you are not collecting photons from the sky, which is the goal of the observations. So,
I have a question.
yes.
Is there a reason you also shorten the exposure period? Like, isn't there enough gain just by shortening the reconfiguration period?
So there is a gain of about 20 or 30%. So in truth, for some observations, particularly of quasars, we actually just do an hour-long or sometimes 2-hour-long exposures. So we do that, but for the goals of the Milky Way mapper, which wants to get like 5 million stars, you have to do the short exposures. And so it's a trade-off. You're doing fewer, you're getting less signal and noise, but you're getting many more stars. And David here and Melissa Ness have taught us that we don't need as much signal noise to get the parameters that we want. Still think that, right?
Yep.
Okay, good. Because we built this thing.
I'm pretty excited.
Um,
By the way, technically, I believe the fiber positioners are Waldos, not robots. Because they obey very well-specified commands. They don't do anything autonomous.
but the PT was a robot? Hog PT was a robot, and this is not a robot?
No, that was also a Waldo.
Okay, good.
I believe. I don't remember exactly. If they really did their own, they kind of do their own path planning. And since they do their own path planning, then maybe they're
Yeah, they don't, no, they don't, that's
It's
true.
pretty-
But it is centralized. Like, there is some server that tells them where to go.
Yeah, so they're really Waldos. Just
They're not autonomous. That's true. Otherwise they wouldn't be doing this at all. They'd decide to do something else.
They'd be mining Bitcoin.
Okay, so
So funny.
so I want to make just one or two more points in the limited time I have. And one point is the following, which is that if you look at the Milky Way, this is my picture of the Milky Way. You have this thin disk, you have this thick disk, you have a halo, you have what's really mostly a bar here, but the bar and bulge region. And, this is more or less what you can see from the north, and the rest is what you can see from the south. And so the reason we have these two systems is to be able to cover the entire galaxy. But when we're doing this, over like 9 years with Apogee 1 and 2, we can only really cover about 2,000 individual fields. And so since each of these fields is kind of like, 4 or 5 square degrees, depending, because you have to average over the north and the south, the total amount of sky you have to cover is 40,000 square degrees. And so you're not reaching the coverage that you need. The point of the Milky Way mapper, and you're getting like if you look at where these pointings are, you're getting some sparse coverage of these various areas. Some places are very well covered, like in the center and in certain other regions, but generally you're getting this sparse coverage.
Change your symbol for square degree.
So it's not,
You're violating the rules of brown bag
who, me?
with that square.
Before it was a square with a circle, now it's a square.
All right, that's a good point. Whereas Milky Way mapper is getting something more like 12,000 fields, and so you get much heavier coverage, a much denser distribution of stars. That also has the consequence that you can actually see further in the galaxy. Even though you're looking shallower, you're looking at lower signal and noise, nevertheless, you can actually see further stars just because you have more stars. Because in Apogee, as 2E's, this ended up being about 700,000 stars, whereas this is going to be something like 5 million. And so you increase that by a lot, and you can see further out into the galaxy. And I want to just talk about one result where doing this can substantially improve, what we understand about something that was new that we learned in the Apogee surveys. And this story goes as follows. One of the things that David and Melissa did, or were part of doing, was that these spectra can be used to get individual stellar ages. So this is Ness et al. 2016. Well, I'll be showing something from Macro 2017. And to greatly, greatly simplify, if we look at radius in the galaxy, not radius from us, but radius from the center of the galaxy, this is about solar. And then we look at the surface density distribution of stars, age measurements, lots of modeling, etc., leads you to a picture where if you look at the young stars, stars you identify as young, say 2 billion years old, their surface density distribution looks like this. They're pushed out in some sense in the outer parts of the galaxy. Whereas if you look at the 12 billion year old population, it looks like this. So this is sort of your classic inside out picture, which is a picture we've had in our heads for a long time about galaxies, but here you see it in the Milky Way by looking at them individually. And at any given radius, there's a distribution of ages, of course, but you see that the center of the galaxy really had its star formation concentrated at the beginning. And then I can look at the metallicity distribution. This is from Hayden 2015. And this is just a distribution of stars. This is my iron abundance. And if I look at these inner parts of the galaxy, I see a distribution that looks like this in the metallicity. But I can look at the ages too. And I will hope I am, this is Diane Fourier. There we go. And there we can look at the mean age versus the same axis of metallicity. And in the inner parts of the galaxy, you see a trend, which if you think about it hard enough, makes sense. It looks like that, which is, sorry, this is -1, this is like whatever it was here, 0. And what you see is that the metal-rich population is younger. It's formed out of gas more recently, gas that's had time to have been enriched, whereas on average, there's a big distribution of ages at each of these. This will become important in a moment. But you see this general trend of metal enrichment with time, because these ages go down as you get more and more metal rich. And you get this asymmetric distribution, which is basically like, yes, there are some metal poor stars that helped enrich your metal rich stars. Whereas if you look at the solar radius, the metallicity in general is smaller, and then you get a much more symmetric distribution. This has been a puzzle for a long time. It's called the G-dwarf problem. It's not fully resolved by what I'll talk about right now, but this is an important part of the story. And so this is the inner Milky Way, and this is the solar radius. Yes, 1 minute. And when we look at the solar radius, what we see is something that looks like this, which is that as we get to the most metal-rich population, you see the ages go up again. And so the question is, where do these stars come from in the solar neighborhood? These metal-rich stars that are in general older than somewhat metal-poor stars. They couldn't have been enriched by these stars because they're older. And the answer is they came from this inner population. Because remember, there's a distribution of ages at each population, so at high metallicity, there are some old stars. Those are the stars that have had time to wander from the inner parts of the galaxy to the outer parts of the galaxy. This was more or less a discovery of apogees, I think. in terms of actually showing it's happening in the real universe. And it's the type of effect which, you know, requires looking at the whole galaxy, being able to measure stellar parameters and abundances, being able to measure ages, and which we would really like to look at in greater detail. Like, does this happen differently in the spiral arms? How is this affected, you know, in and around the bar? Are there structures that are not in the density but are in trends like this? And this larger sample is going to allow us to delve more deeply into questions like this. An hour. Questions for Mike?
So
Yes.
you briefly mentioned Gaia at the beginning. But Gaia has a catalog of more than 1 billion stars,
Mhm.
right? And you mentioned that it also collects some spectral information, things like that. So sort of what exactly does this do better than what Gaia can do with their massive catalog?
So what it can do, so it's not as large as Gaia for sure. What it can do are mainly the actual finer abundances than this. So you can take this story and you can say, oh, let me look at the, you know, like the alpha elements like magnesium, oxygen, and look at those trends, which is, you know, a whole nother complication of the story. And then, but then there's like 15 other elements which either follow, you know, iron or follow the alpha elements or do their own thing. And those are telling us about more details about the enrichment and about the galactic history. And so Apogee gives you access to those things. It also gives you more precise radio velocities, and it observes the plane better as well. So luckily we don't have to choose. We have both. And so mainly the question we worry ourselves with is like, what should we be using from Gaia and Apogee together in order to measure like the 6-dimensional, you know, phase space distribution of all the stars and all the properties.
Are the radial velocities, is there a large overlap between Gaia and these 5 million stars? Radial velocities, or are they separate?
Do you mean, are they, well, basically everything we observe, I don't know if it's quite true that everything we observe, it has something in the Gaia catalog, but there'll be a large overlap, yeah. What's the Gaia radial velocity?
The radial velocity sample will fall apart in the center of the galaxy. So in the
For
thin
Gaia.
disk in the center of the galaxy, I don't think Gaia will give us radial
What's the
velocity.
precision of Gaia for radial velocities?
Similar to ours, I think, but they're single
Like
shot.
a 100 kilometers per second?
No, it's not that good. It's like whatever, hundreds of,
Okay.
or like whatever, 1 kilometer, like 5 kilometers a second. I don't know. It's like
Yeah, so I think the Apogee is, I mean,
more
They're
accurate.
more-
And
they're-
there's more epics.
they're high resolution spectra.
Maybe you said this in a mistake, but at the beginning of your talk, you mentioned it was time domain-ish. But why does it earn that title?
It earns that title because in order to observe, I mean, just sort of built into this is in the center of the galaxy, there are lots of stars, more than 300 per few square degrees. And so you have to go back many times. And so that gives you an opportunity in those parts of the sky, and we choose in other parts of the sky to go back to the same stars over and over again. And one of the main things you want to do with that is look for radial velocity variations. And the precisions are, you know, of order 100 meters per second. So you're not looking for planets generally. You're looking for you know, substellar companions or stellar companions. But that's why I said time domain-ish, because there are parts of the sky which we go, you know, over, well, we certainly go over many times and repeat the spectra of stars. And what I didn't talk about, the black hole mapper part of the program, like that's what they do. They observe quasars over and over and over and over and over again. So they'll do reverberation mapping to get black hole masses out to redshift 2 for like, I don't know, 500 quasars or something like that. So it is time domain, but it's not time domain in the sense of like, it's not both all sky and time domain.
But if somebody wants to pay us a few million to do more time domain, we're open to it.
Are we?
I
Okay.
think so, yeah. That's what Juna and Rick's tell me.
Okay, then I'm more open for this.
If anybody needs time domain and has some cash.
Anybody have some cash or another question? Let's think, Mike, again. There should be some cookies and espresso.
Is that a longer?